to have you with us. Yeah, I hope all of you will have a great learning session with Dr. Chandrasekhar. And yeah, on the outset, I would like to thank everyone, and also the outline of this program I already discussed. So we will be discussing machine learning, geospatial technology, and then we will be moving on to the supply chain talks by the experts. So by then we will have a strong background in ML and GIS. That's the aim of this 1 week session. Then we will have talk by the experts in the next session from 20th to 25th. Thank you all once again, and thank you, Chandra. So over to you, Chandra. You can briefly introduce yourself and you can start. Thank you. Thank you so much.
Hi all, good morning and welcome to this FDP. So,
yes.
Surya.
Keep it here, sir. No, from here. I just downloaded it. Sure. Password. Yes, sir. It's not one.
Hope am I audible and visible? So we have seen that
So screen is not this.
need to share the screen.
Okay, this one.
Okay, so wherever, not only specific to supply chain, wherever there is a data, so there is a huge chance of analytics and extracting the information out of data. So any area like business to business analytics, supply chain management, marketing, retail. Okay, so if we have a data, the ultimate aim is to extract the features, the information about data. Okay, so for that we have traditional classification techniques. Slowly, with the advent of APIs, memory, CPU, we have pattern recognition, machine learning techniques, and deep learning techniques. So compared to traditional and classical techniques, machine learning plays a major role in extracting the information. Close the doors. Close the doors. Nice. So compared to classical and traditional techniques, okay, so machine learning techniques, okay, so helps us to perform optimal analysis on the data and to extract features, okay, and we can perform various techniques, tasks like poor resource planning. So how to overcome with resource predicting. Ultimately, the aim of machine learning or deep learning techniques is from the past data, how to predict the future. Okay, for that, which are all the various techniques we can use, especially we are using machine learning techniques. Okay, so specifically in supply chain, not specific to supply chain or any area. We can use for resource planning, how I can optimally use my resources, predicting, okay, planning, predicting, all these which are unseen cases, we can use machine learning techniques, okay. So here we are mainly focusing on what is machine learning and what are the main ideas of machine learning. And here the approach is towards mathematics. It's this session is not coding oriented. We will look into how mathematics or statistics is part of machine learning, and how can we use machine learning, means the math plays a major role in machine learning, and how it decides the optimal learning process of any models. So we look into fundamental concepts in statistics, linear regression, gradient descent, decision trees, and neural networks. So here, first we look into what is machine learning. So first I will glance through all the slides, so you will get an idea of what we are going to discuss in this session. So these are all the slides. We'll come back to each slide. So first I'm glancing so that you will come to know what actually it is, pure math-oriented slides which we are going to discuss. There is no code. Okay, so we discuss the statistics, probability. Okay, we discuss probability, linear regression. We look into decision trees. We look into gradient descent. Okay. Nice, guys. Okay, so complete end-to-end math. So there is no coding involved in this. Okay, so this is what we are going to study in this lecture. So this is pure machine learning. The focus is on mathematics. Okay. So now, first look in machine learning. What actually machine learning? See, machine learning, what is learning? So learning is what similar to how a human being learns. He is having some past experiences. From past experiences, he will do some learning, and based upon those learning from the experiences, his behavior changes, his decision making will change, and his outcome will change. Similarly, same kind of human learning we want to incorporate into the machine. So how it works? So machine, see, for us, for human being, we have past experiences. For machine, everything should be in the form of a data, numerical data. So from the data, we want a machine to learn. What is learning? Understanding the hidden patterns in the data, and based upon that, it has to come up with the decision or the outcome or the behavior. So making a machine to learn as how a human learns from behavior is called as machine learning. Where a human being learns from past experiences, here a machine learns from data and rules, means mainly data. So what does machine learning look like? So in machine learning, the goal is prediction or clustering. What prediction means? From the existing data, from the seen data, from the current data, we need to perform some analysis, and we want to predict into the future, unknown data. That's why the machine learning and deep learning experts are in more demand. Why? Because they need to predict what is going to happen, when the defect will occur, or what are all the needs of a customer, what will be the stock price, what will be the volume, what will be the next starting price, how many goods the next day are in demand. Okay, what is the click rate of an advertisement? So all these things we need to predict upfront based upon the previous data, previous behavior of the user. So that prediction what makes the machine learning challenging and in demand. Okay, so using a set of characteristics of a house. Characteristics means features. From data, we need to get features. From features, we need to predict. So predict means unseen. Okay. Similarly, we have unsupervised techniques. We'll see in the later part of the course. So what are the main steps involved in machine learning? So one is defining the goal. So means the problem needs to be solved, and the data. So because of the real-time data is always challenging, always with outliers, always with noise, incomplete, and not fit to feed into the computer or a model. So we need to perform pre-processing techniques. Based upon the pre-processing techniques, we need to build the model. Okay. And then once the model is built, what is model building? Model building is we want to mimic a human learning. We want to make the model, okay? Means here when we say a model means an artificial human learning, human mimicking is happening. So they learn the features from the data. Once the learning is done, we evaluate because we want the accurate predictions. The outcome from the model should be accurate. So the evaluation, we will evaluate out of all possible models, which is the best model we will select. And then based upon that, we will use it for inference or testing and for further processing like interpretation, etc. So these are all steps in machine learning. So what is machine learning means? Making a machine to learn similar to a human being from the past data and helps us in predicting a future unknown or unseen data is called as machine learning. So here, Surya, can you switch off those fans? Nice. So here if you see, we have an algorithm. Okay, so we'll just see what is machine learning model and a machine learning algorithm. So always any learning, we need to have data. If we want a machine learning model to learn, we need data. From the data, we need to extract the features, the patterns, the hidden correlations between the features. So where we will use the mathematical formula and then we'll develop the model. When we say model, it is a mathematical equation. So when we say machine learning, which is equal to a model, which is equal to a mathematical equation. So ultimately, when I say learning means a mathematical equation is ready, which learned the correlations or the relations or the hidden patterns among the data. Okay, so machine learning is nothing but for a problem to be solved. Okay, we have a mathematical model ready, which reflects, which learned the patterns, the hidden patterns among the data. And once the mathematical model is ready, so we will use that model for prediction. So preparing this model is called as learning. What learning? Learning from the data. We have a data and we want to give accurate predictions. How to transform the raw data into accurate predictions? It happens through the model, and that model is a mathematical equation. Learning this mathematical equation to accurately convert the data, the raw data to prediction is known as machine learning. So while transforming the data, we will follow some set of steps, which we call it as a machine learning algorithm. And finally, we will come up with the equation. So here we use an algorithm to transit the data to an equation. Okay. So ultimately, whenever we say there is a learning happened or there exists a model, either it is a machine learning model or a deep learning model, there exists a mathematical equation. That mathematical equation must give accurate predictions, accurate output. When we say accurate, there should be some series of steps to be followed. Okay, so we are going to see. So here we understand that whenever we say machine learning, it is mathematics. So how mathematics forms the basics of machine learning, we are going to look into the we are going to look into this session. Okay. So building the model. So why we need to build? See here what happens at every stage we have some steps. So how to collect the data, how to pre-process the data, how to make the data ready to fit into the model, and how to validate the model, and how to predict. All those things are forms part of the machine learning process. But here in this talk, we are completely focusing on the model development and how we are going to look into how mathematics plays a major role in developing the models. So building the model. So before going to, when I want to build a model, first thing is I need to have a problem. To solve a problem, I need to have a data. Okay, so this is the data I have, and there exist 4 features, a table data, age, gender, smoking, vaccination. These are all the 4 features, and I have a label. So now the problem is from these particular rows, how many rows we have? 6 rows. From 6 rows, it has to understand the correlation between why the first row is mapped to 0, why the first row is mapped to 0, why the third row is mapped to 1. So it has to understand why between, what is the correlation between age to gender, what is the correlation or the dependency or the relation between gender and smoking, age and smoking, age, gender and smoking. So various combinations it has to learn and also the mapping between a row to column. Why this combination mapped to 0? Why this combination is mapped to 1? And like this, see here it's a female, here it's a male, but still both are mapped to label 1. So model doesn't understand the domain meaning inside. It understands only the correlation or dependency between the data. Okay. So whenever we have a data, those problems are called as supervised learning. So in case of supervised learning, we have a guidance, we have a supplement or additional information in the form of a label. So what are the problems we can solve with the help of a label data? We can solve regression problems or classification problems. So we all know that regression problems means we want to predict the unknown data from the past data, from the past 5 days of temperature. Is it possible to predict the 60-day temperature? From the past 7 days of sales volume of Pepsi bottles, is it possible to predict the 7th day volume of Pepsi? Okay, so predicting the numerical value is known as regression. And what is a classification problem? Classification problem means assigning a label to one of the class. Whenever we give a test sample, assigning a label to that particular data point, we want to assign one of the class. So assigning one of the class to a data point is known as a classification problem. So that's all. We can do it if you have a labeled data, and that's what we are calling it as a supervised problem. And in case of a unlabeled data means we don't have any extra information, that is labeled data. So that's called as a unsupervised scenario, where unsupervised means we don't have a guidance, we don't have an extra information, that is a label. But still, without label also we can perform certain tasks like grouping the data or reducing the reducing the number of columns of the data, finding the best set of features. So all those things we can do it from the unlabeled data, like grouping of the customers, okay, and which are the best features, deciding the best set of customers going to purchase a product. So all those things we can find it out from the unlabeled data. So what is a regression? So a regression problem, all these slides I have taken from the net, and nothing is my own. So here what happens, a regression problem. So what is regression problem? We have some predictors. Some predictors means some examples. So here, when number of hours he studied and number of hours he slept. Based upon that, we need to predict the result. Okay. So to predict, we need to have previous data. What is this? Like this. If we have some previous data, then only a model will generalize the unseen scenario. So a model without learning, without seeing the past data, it cannot able to answer the test cases or test answers in unseen scenario. So the first step in any learning process is, see, whenever we are saying learning means there is a source that we have to learn so that we can able to answer the unseen scenario. What is that source? Is data. So we must have a similar data, and the model has to learn the features, correlations perfectly, and then it can able to answer the unseen, or it has to generalize the unseen scenarios. So here, these are the columns, or these are the features which we feed into the model. So when we plug in these values, it has to give a numerical value related to the input. So those scenarios we call it as a regression problem. Or suppose if we say some features, if we input regarding a house, so what is the selling price? What is the maximum selling price we can quote for a customer? So based upon the features, number of years like an apartment, how many years it was purchased, it's a 2B or a 3B, or what is the prime location or not. So based upon all those features, we can able to find what is the maximum amount of what is the maximum selling price. So all these unseen scenarios we can able to find out from the past data. Okay, so regression is such a problem. And classification. So classification is what the labels are fixed. So the features remain same. See, hours of study and hours of sleep is same both in case of a classification problem and in case of a regression problem. But what is the output? The expected output is what makes the problem different. When we are expecting a single numerical value, we call it as a regression problem. And when we are doing, when we are expecting a class, what type of a class it is, whether it's success or a failure, or spam or unspam, malign or a non-malign. So all those things we call it as a classification problem. Means we have to assign a label to the available classes. So that's what a classification problem. So here also, rather than predicting the exact market value, if you want to assign based upon these features, it will be the features represent that the price of the apartment is below the average value at the market price, or exactly the market price, or above the market price. So we can assign a class, or we can predict an exact value. So what are the terms that we are going to frequently use in machine learning, or a model? So a model means like we have from program point of view, okay, we have classifiers, SVM classifier, regression tree classifier, binary tree classifier, neural network, CNN, RNN, etc. From from mass point of view, every model is forms a heart of learning. That means the mathematical equation forms the heart of the model. So mathematical equation forms the heart of machine learning. So how to frame the mathematical model, and any model, how to represent mathematically, is what we are going to study in this lecture. So what is training? So training means, as I said, given a set of data, previous data, or a seen set of samples, we want the model, we want to develop a model such that it will learn the features from the data and able to predict the unknown or unseen scenarios. And what is a classification problem? As we have seen, assigning the label to one of the class is called as a classification problem, and predicting a value from the trained data is called as a regression problem. And what is a target? Target is called as a label. So here in case of a classification problem, the label, or we can call this column as a target column. Test set. What is test set? Unseen scenario, unseen case, we are calling it as a test set. Okay. So what is training set? The training set is what we are using to train a model. So the trained data we use to feed into the model, and the job of the model is to follow an algorithm in order to understand the correlations between the features and the target label, and the mapping, why the row is mapped to a particular target value. And what is a feature? The descriptive characteristics of each data item, we call it as a feature, and how we represent in the how a feature is represented. A feature can be a column. Here each column represents the feature of a sample point or a data point. Each row is a sample or a data point, and the sample is a collection of 4 features. So attributes or columns or characteristics represent the same, and the row represents the data point or a sample point. It's a part of a domain which we are going to study. So algorithm is what we use to follow in order to make the model learning optimal. So learning forms the core of any machine learning activity. So how to learn? So how to systematically learn those correlations, the dependencies, the relations among the data is what we call it as a algorithm. And what is overfitting? So all those terms which we see. So these are the main terms which we use in a machine learning jargon. So which are all the algorithms as we discussed? So linear models we have. So any problem, when we want to apply machine learning, some learning over on it or on the data. So we have linear model approach where we develop a linear equation, and a tree-based approach, tree-based models, where we develop a model which looks like a tree and a decision will take, and neural networks approach. So in neural networks, again, we have neural networks and the deep learning scenarios, like deep learning networks, like convolutional neural networks, RNN networks, CNN, advanced like transformers, etc. Okay, so all those things we'll see. So when it comes to prediction, we have linear type of, the model, which one to select, it all depends upon the data. The data distribution determines which type of model we need to select. It's not the model we select and we apply to the data. So we have data. Ultimately, the aim is to transform the data into a model, and the model has to predict. So all starts from the data. So depending upon the data, by analyzing the data, which distribution the data is following, we need to select the approach to solve the problem. Solve the problem means either prediction or classification or unsupervised. So it all depends upon the type of data. So once we determine the type of data, then we can choose the technique to adapt to solve the problem. So here we have linear type. So it can be a linear equation depending upon a simple data, as I have shown here. These are the data points. For these data points, I can fit a simple linear line. So once we fit a linear line for the data points, and the model, if it model learns a line from these data points, then what is the advantage by fitting a line to the data points? What is the advantage we have by fitting a linear line among these data points?
Prediction. Right prediction.
Right prediction means? So why we need to fit anyone from the online? So what is the advantage if I have some set of data points? I hope it is clear. So some set of points here, blue and circle. So when I say linear learning algorithm, we fit the best fit line for these data points. So when we fit this line, what is the advantage?
All data in under control level.
Okay. No, I'm asking about advantage. Next, what we are going to use. See, I fit the data. Then why if once I fit a straight line, and when I'm saying that this straight line best represents the data points given to me in the training set, then what I'm going to use, what I'm going to do with that line?
We will get a equation. We will get a equation of the line, and that could be the regression equation.
Linear regressions.
Okay, so that line, straight line is having an equation y equal to mx plus c, where m and c are the parameters needs to be learned by the model. So by performing some gradient descent, which we'll see, some algorithm, we will select the best fitting line to those data points. Once we have that straight line, I can plug in any set of x values, unseen values, I can get y values. That's what she said. So once from the training data, if we fit a straight line, then that straight line can be extended and I can plug in any x value, I can get corresponding y value. That's why we need to find out what the best equation for the data points. So once I can able to fit a line, then I can extend any the x-axis to any point, and when I plug into that particular equation, I get corresponding y value. So from the training data, if I learn the best fitting line or a best fitting model or a best fitting equation, then I can able to predict infinite unseen points or predict the unseen points. So why I'm fitting this line? Because the reason is the data is linear. Here the data is linear. So if the data follows a linear distribution, I can draw a linear line which is best fit to this data distribution. Okay, so x-axis we are called as a independent variables, and y-axis we call it as a dependent variable. Y equal to mx plus c, where x is independent variable, you can plug in any set of values. Depending on the independent value, we get a dependent variable y. So what is the problem here? What is the problem we need to solve while fitting a line here? What is the complexity? When we talk about fitting a straight line, what is the step to be followed? Important step. See the data point we have here. Is it clearly visible? So here we have the data points. Here we have the data points. Cursor is not visible, right? There it's visible. Okay. So here we have data points. Here that means it represents an x and it represents y. So we have x comma y coordinates. So based upon the x comma y coordinates, we were able to plot a line. Then what is the important thing here? We have x comma y. That x comma y we need to transform into y equal to mx plus c. Right? So what are the important things? What are the crux in this forming a line? Any online participant? Hope you got my question. I have some set of points, x1, y1, x2, y2, x3, y3, and that is raw data. and some learning to be happened, so that suppose if I have 10 points, x1, y1, x2, y2, x10, y10, till x10, y10, so we have 10 data points, and I want to predict from x11 to x20 or x11 to x infinity. Then what is the first step? We need to fit a line. Assume that the data is a linearly separable, or sorry, that's linear distributed, so I can able to fit a line. So when I say line, that is yi equal to m into xi plus c. So xi comma yi is transformed into yi equal to m into xi plus c. Now what is the crux here? What is the important thing to be done?
We have to get the value of m, and then we can draw the line.
The value
Yes.
of both m and c.
Because it
Yes.
will, in the
But C will be 0.
See, the equation is y equal to mx plus c. We have x comma y pairs, and by using these points, we need to fit the best curve. When we say the best curve, based upon m and c. So we have raw data x comma y, some set of points, and ultimately we are converting from those data points we are learning, and we are framing a straight line. That forming a straight line is called as learning, y equal to mx plus c. X and y is already given. So what we have to learn here, m comma c. So m comma c we have to learn optimally, so that the predicted values of unseen cases should be as accurate as possible. So where learning happens here, learning happens in getting the best m comma c with the help of x comma y, the training set given, so that the next set of values are predicted with less error. So learning means m comma c. So if I know m comma c, I can able to fit the best curve. So learning the best curve is again equal to learning best m comma c. So then we can say that a model is ready. Okay. So some set of points we have. When we say a model is ready, then we are saying that a linear equation is ready, a straight line is ready. That means m comma c is ready, because x comma y is already given. So no need to worry about x comma y. The ultimate aim is to find out m comma c. So why we are able to fit a straight line? Because the data points are linear. Assume that the data points are not linear. In all the cases, it doesn't mean that we can come up with a, we have
Sir, need to maximize the screen, sir.
this one.
I mean this one, I think. Maximize option is maximize option is available.
I don't know.
Maybe this. Just
Here. Max வரல மேடம்.
சரி, அது இந்த ப்ராஜெக்ட் பண்றதுனால நமக்கு தெரியல.
Mouse here.
other mouse sir. Sir, I just did hide presenter view கொடுத்து பாருங்க. Okay.
Okay, so here we have some set of points x comma y, it's already given. Say I equal to 1 to 20, that's it. Those are the raw points. So ultimate aim is I want to predict x21, like we have x21 comma y21. So like this we have some infinite set of points. So what we need to do, this is the expectation. We want to predict the best y values in unseen scenarios. Okay. Now, so what we need to do, always learning starts from some seen or some trained data. So what is the learning here? What is the proof of learning? This is a source of learning. The data we have is source of learning. Then what is the proof of learning? Or the resultant of learning? Resultant of learning is to coming up with a straight line. So what is the advantage of straight line? What is the advantage of straight line? I can extend to any infinite point, and for that infinite point, I can able to find out what will be the unseen value. So till here, this is till here is seen data, and from here to here is unseen data. So that is what the power of machine learning. So how to do machine learning? I need to have a model. Once I develop a model, I can plug in the data. I can plug in any somewhere here, I will plug the data. Then what is this corresponding value is the y value. But I have seen only till here. But as I can extend, I can plug in any infinite value, I can get y value. But how I can able to do the, how I can able to present a straight line here? Because the data points are linear. Assume that we don't have a linear separation of points, then what we can do? We need to learn a non-linear curve. That's what we are going to see later. So this is about linear regression. And what about logistic regression? So a logistic regression is also a kind of a problem. Okay, so here what happens? We are trying to see rather a linearly separable curve. The blue line indicates a linear curve, but here we are fitting a S-shaped curve. Okay, so this S-shaped curve assigns a value between 0 to 1. So if it exists in two cases, the regression becomes a classification problem because it has to assign a value either 0 or 1. In those cases, it becomes a classification problem. So the adaptation of linear regression to problems of classification. So yes or no, okay? Two cases, if you have two cases, either 0 or 1, then we can also use a logistic regression, where a logistic regression fits a S-shaped curve to the data points. And once we know the curve equation, what is the curve equation? See, in case of a linear, this blue equation is this one, y equal to mx plus c, or y equal to b naught plus b1 into x. So the learning is b1, b naught, b1. X is given, y is given. If I want to learn a straight line, I need to learn b naught and b1. That's called learning, machine learning. And here we in logistic model, we need to learn, we have x, if we have x, okay? So this is from x and y, we need to learn the probability. That is 1 by 1 plus e to the power of minus b naught plus b1 into x. So b naught, b1 are the points to learn. So ultimately, when I say a linear regression model, there exists a mathematical equation. When I say a logistic regression model, which claims result means between 0 and 1, a probability of 0 and 1, okay, there also exists a equation. So whenever I say model, there exists a mathematical equation. So that about linear. Suppose we also have tree-based models. So where we have decision tree, random forest, and gradient boosting, which we'll cover in the due course. See here. So we have a tree. Okay. So these slides are also taken from net. So nothing is mine. So here we have some decision making, either yes or no. If I am clear, if the leaf is clear, we will stop. Again, if the decision is not clear, again we'll go to the left side, right side. Again, we need to go with yes and no case. If I have a clear decision making leaf, we'll stop here. Else I go further. That means if I'm not success with the first step, then I will go for second step. I will use second feature. Then I will use third feature. By using some set of features, finally I will come up with a decision process. So all these things we are going to study in deep. So similarly, we have random forest, okay, and also gradient boosting algorithm. So tree is the basic structure or the basic classifier. This tree we are resulting into, based upon this simple structure or simple model, we are developing the complex models like random forest, gradient boosting, etc. Okay, we are going to study in detail. Next. Non-linear, complete non-linear. So tree-based decision making, linear decision making. So here we have non-linear models like neural networks, where if you're unable to fit a linear curve, if you're unable to fit a logistic regression, and the data or the problem doesn't fit into a tree decision making process, so we need to learn a complex equation. Okay, so say that, see, this is a linear equation and this is a logistic equation. Assume that there exists a complex equation. Okay, so what is that complex equation? Say like this. So this is a complex equation. So how to learn this complex equation? This is very simple. Okay, so the data here we have data. So that if it is simple data, I can able to fit a simple straight line, and that becomes my model. And if it is okay, if it is only 0 and 1 case, two class problem, I can fit a logistic curve. Or if I make a decision making process, if I can able to come up with a label, then it's a tree based. assume that because the real-time data, okay, the Flipkart transaction process or the Amazon transaction, the sales, okay, so all those things are very complex. It's not possible to fit in a simple curve. See why I'm talking about curve? Ultimately, the curve or the equation represents a model which represents learning. So if my data points here is such a way that if my data points are separated like this, in this way, then I need to learn a complex curve. Learning this complex curve is not possible with any linear or a tree-based structure. Suppose if we try to learn or if we try to fit a tree-based structure, see this is the data points I have, and if I put a tree structure, then what is the problem? There is far separated points. So this is what is a straight line represents. Straight line represents a set of what a straight line represents in a linear regression. A linear regression, a straight line represents a set of. Can anyone answer? It's not. Can you please repeat? So my question is, suppose we have a straight line, linear equation. In case of linear regression problem, we come up with a linear line. What this linear represents, this linear line represents. This linear line is a set of what? Which data points? Yes. Input then. X then.
The set of X and Y. Yes.
So the straight line represents a set of predicted points. The actual points, see in a straight line, these points, this blue point represents the actual points. And the straight line, this line represents, it's a collection of predicted points. The difference between the original points and the predicted points represents the error constituted by the line. Okay, so the line represents a set of predicted points and original points. The difference between this point, okay, this point error is this one, okay, because this represents a predicted point. See, this is a point where the predicted point is here. The difference between these two is an error, because a straight line represents the prediction of each original point. That prediction error, the difference between the line and the point should be as minimum as possible. But it's not possible to fit a completely matching line. So with a minimum error, we can able to fit a straight line. Okay, so here what happens? So if we fit a straight line, see in this case, whenever we fit a straight line, the straight line is a collection of predicted points. So this is a predicted point, but actual point is here. So what is this? This we are calling it as a error. So this and all error. So the error will be high. For this point, it is here. For this point, it is here. For this point, it is here. So this constitutes a very huge error. So this model is not optimal or not valid to deploy in real-time scenario, real-time like a vehicle, like automated vehicle driving. In those scenarios, okay, these models are not optimal. So we need to learn a function which will learn this kind of high-level, high-dimensional, non-linear curves. For those learning, we need neural networks. So what neural networks learn? So neural networks like this, it able to learn low-level features. So from this particular image, okay, so what it will do, it will break the image, okay, it will break the image, and like this, it will break the image, and it will try to learn the features. This is one feature, okay, this is one feature. So like that, it will learn the lowest level features first, and then combine them to form complex features, then combine them to form complex features, and finally it will combine all those features to finally come up with an image. So it will what the neural network will do is it will learn the minute points, presence of any horizontal line, vertical line, circle line, dashed line. So all points it will check, and it will keep on combining them, and finally whichever points are present, corresponding output it can able to frame at the end. Based upon that, it will assign the class. So learning these kind of points, these kind of images is not easy. Is not easy as this set of points. So based upon the data, based upon the complexity of the data, distribution of the data, we need to select the model to work on. So if it is simple point, we can use a simple linear regression, or if it is a tree-based decision-making columns are there to come up with a decision, yes or no, then we can go for tree decision. Or if it's a very high complex problem with learning curve fitting of high dimensional curve fitting, then we need to use neural networks. So is it magic? No. So see here, we have built-in functions. So whenever we say linear regression, I can import linear regression. So we no need to know what is linear, what is regression, and what is curve fitting. We no need to know anything. We no need to analyze anything. Okay, so Python provides everything to us. So we are just using sklearn linear model, and we are importing linear regression. And based upon the linear regression, we are fitting the points, and we are getting the length model. Then why we have to learn the mathematics behind it? Why we need to learn? Can someone answer this? Because everything is available as single line statement, then why we need to learn those mathematics behind the models? Can someone answer?
Constraints.
Huh?
Constraints.
Constraints means?
Mathematical model we have some constraints.
Okay. Constraints. What are those constraints?
Equality.
Huh?
Equality constraints.
No, not constraints. Constraints, see, the data we have, we are able, here we have linear regression. We have x comma y. This x may contain those constraints, but still we can able to fit the curve, right? It is taking care. Similarly, we studied.
If we know which model to use, we'll be able to use these functions.
Fine. We have, say, linear regression, logistic regression, decision tree, 3 models are there, neural networks. So if suppose if I have 10 models, so each model will take 10 minutes. So in 100 minutes, I can able to come up with the best model. What will happen? Nothing. So why? See, logistic regression. So logistic regression also, we no need to worry about what is this curve. Okay. So this is logistic regression. Instead of fitting a straight line, we are fitting a logistic curve. So why we need to fit this, and why we need to learn this model? So built-in is available. So we can use this built-in function in a simple line, in a single 2 lines. We will able to load iris data set, and we can get the x comma y pair. We are fitting x comma y pair, and we are getting the model, and model I can use it for prediction. So why? Then everyone can become a machine learning engineer in 5 minutes. Then why we have to learn? See, this is what we are going to study. This is linear regression, logistic regression, decision tree, gradient boost, random forest, and neural networks. All are there with simple this one. So why in every 5 minutes a layman, a LKG guy can become a machine learning engineer and apply for Microsoft? So why it's not happening? Can someone answer? Why this is happening? So why we have to learn maths behind it? So everything is there. Whatever we spoke about, linear regression, fitting a model, logistic regression, decision tree, gradient boost, and random forest is there. And we also have dense layers. Everything is available. So why we need to learn mathematics? Tell me. Then we can go ahead. Why we need to learn mathematics? Because first we need to know why we have to learn mathematics. Okay. Now here we don't need to worry about algorithm. Okay, if you're interested, you will learn. If someone is not interested, also fine. He will just plug in. He can do it. You are interested in learning the structural algorithm, so you will go ahead and you will learn the structural algorithm. But without knowing structural algorithm also, you can able to solve the problem. So why we have to learn the math behind it? If you can able to convince that we have to learn the mathematics, then we can go ahead. Why we have to learn the model? That is my question. Right? Everything is available, and this is also not much complex. Simple, just 3 lines. 2 minutes. We learned this. 2 minutes. 2 minutes. So 1, 2, 3, 4, 5, 6, 6 into 12, 12 minutes. So 12 minutes we can become a machine learning engineer. 13th minute we can apply to Microsoft. Why that is not happening? I want one reason. Why not everyone is applying? Or why they are not taking everyone?
Error calculation.
No, why I have to worry about error calculation? Regression is there. Assume further steps also available. Because of space limits, I written till here. Everything is available. Assume model is REG. From that model, I will predict and then I will do it. See, the reason is, here if you see here, we have load iris. Iris is a built-in data set. It's a ready-madely tuned data set. So first data set, we may achieve 98% accuracy. But real-time DMART transaction analysis, real-time ICICI Bank fraudulent analysis, real-time data is much worse. They are getting accuracy of 60% is a very great achievement. So all these mathematical models we are learning with the help of well-curated data sets, well-structured data sets. It's like ready-made apartment which we can move on. But if we want to construct from scratch, so we have to know end-to-end. So the data sets which they give while learning the machine learning, well curated, well available, well balanced data set, so that the mathematical models are able to learn perfectly. It is very easy for these models to learn from those data sets. Assume that we have class imbalanced data sets. Suppose out of 100 columns, okay, so 30 columns are not given for all the data items. Suppose 1000 rows I have, 1000 rows into 20 columns. Okay, assume that for each data point, one of the column value is missing. Because in real time, it doesn't mean that for every column, for every row, we need to have a value. There will be noise, there will be outliers. In those cases, how to solve the problem? See, these data sets, they are not working on cancer detection. Why they are not working on cancer detection? Because cancer detection doesn't have much data to work on. Very rare to get those data types, data sets. So for those data sets, getting an accuracy of 50 to 55% is very high. So real-time data, the companies or the problems which we are going to, like the data set representing the real-time problems are far complex than the data set which available to us while learning any course. So if we assume that by playing a video game that we're not driving, and then we start driving a real scooter, that's it. Same scenario here. So we are learning all these things are like a video game. This is real time. So there is a far difference between playing a video game and coming onto the road with a real bike. So we have to know end-to-end what is happening, and any data set like cancer data set, imbalanced data set, assume that one class is having 1 lakh rows, 1 lakh labels, another class is having only 5 labels, but still we want to achieve accuracy. So how to do that? So those are the cases where real-time companies or real-time environments try to solve, not these iris cases. Iris cases are like a video game where everything is there, we can learn. So without understanding end-to-end, like if we what is a brake, what is a speed, what is escalator, without knowing anything, if you come to drive on a highway, how risky it is. Same here also, by learning all these 5, 13th minute if you go that I know machine learning, same risk. So we must know what is end-to-end mathematics behind any model, so that you can make the model to work for any kind of data set. If you luckily get a load iris, yes, you will win. But if you unlucky, if you get a Flipkart data set or Amazon data set with millions of rows and hundreds of parameters, and you want to predict the future, in those cases also your model has to work. For that, if you know inside mathematics, then you can able to optimally tune them, modify them according to your own logic, and come up with an optimal solution. Okay, so that's why you need to understand, say machine learning is like a bike. You must know, and suppose in highway, if it stops, you must be able to repair it and go ahead. So you must know end to end, what is there, what is the meaning of each, what is a brake. Okay, similarly, what is a variable, what is this variable is doing. So on road, what to do, on mountain, what to do, on a desert, what to do. So different data sets you must know, and you must be able to drive. So same case with the machine learning also. In any, we are just using load iris is just a video game based road. So we are driving. No, on mountain and hill view. So how to do this on sky also, the bike, you have to drive the bike. So in those scenarios, how to work on. So for that, you need to have end-to-end understanding of the bike. Similarly, the model. So what is ultimately inside the model? Mathematics. That's what you have seen. So you must know what inside the mathematics, so you can save your life. Else it's all gone. It's like a toss. Okay. So with this introduction, we are moving to importance of machine learning. So how important is a strong mathematical background in machine learning? So a famous professor, Sridhar Mahadevan from Rutgers University, is telling that mathematics is a language that modern machine learning is built on. So machine learning is built on the mathematics. So trying to do machine learning without knowledge of math is like trying to play classical music without being able to read scores. So in essence, machine learning is about extracting structure. You need to extract the structure, then only you can able to come up with a model from data. So data is the starting point. From data point, you need to extract the structure, like finding the patterns, hidden patterns, correlations, etc. They may contain great deal of noise, great deal of missing values, unfit values. Okay. So nothing prepares you better. You have to prepare better for a lifetime of doing machine learning as a deep knowledge of math. Okay, so have you convinced? Have you convinced? So now what is the important thing is not using these. This is like an RMP doctor. To some extent, these can save you. But if it serious case, we have to approach MBBS MD. So that is what a person who knows machine learning plus mathematics. This guy knows only coding. Okay, so model means ultimately, model means set of mathematical equation. This is an equation. So this y is the predicted value, and this x naught is the data point. Okay, so data points are given to us. These data points are given to us, and y is also given during the learning phase. And we have to come up with this equation. Now, what is learning here? When I say learning, what actually the learning here? Yes. So when I say learning, ultimate aim is I have some data. That data I'm representing as x1 comma y1, x2 comma y2, xn comma y1. So this data is given. What is my ultimate aim? Ultimate aim is if I give x of n plus 1, I want to know y of n plus 1. So I'm assuming it's a linear equation or whatever it may be. So this is an equation. If you plug in some set of values, it will give you the y value. Because it's a multi-feature equation, right? It's not a linear equation because multiple variables are there. High-level equation. Okay, not a linear equation. This is a non-linear equation because we have multiple features involved: x0, x1, xn. So this is a non-linear equation. So if you substitute these features, you will get y value. So these x0 and to x10 is given. Y is also given. So what we need to learn? We need to learn weights and biases. So learning, when I say that my model is done, means I am done with the learning of weights. So machine learning means ultimately boils down to learning weights and biases. If you know weights and biases, you will come up with the model. So this is a model. Once you get the model, you will substitute the values and you will get out the output. So ultimately, machine learning means weights and biases. How you will know weights and biases? There exists some structure, some set of rules to be followed mathematically. Okay. So with this conclusion, we are moving to next part, like What's the time now? So 12 will have break. So machine learning is 4 pillars you must know. Okay, statistics, I can say math. Okay, probability, calculus, and linear algebra. So without knowing this is like brakes, this is brake, this is about engine, okay, this is about seat, something like this. So if you know all these things, generally you know about bike. So you must know statistics, probability, calculus, linear algebra, then only we can say that you're a machine learning engineer. So fundamental concepts in machine learning, this is what we are going to start. So ultimately, what are steps needs to be followed? What should be the aim in machine learning? What should be the aim in machine learning? What is ultimate aim in machine learning? When we say that I'm solving a problem in machine learning, what is ultimate aim? What is internally what is happening? When I say
Mathematical.
ultimately my aim is to learn the mathematical equation. No model. Machine learning means model. Model means mathematical equation. Mathematical equation means in that known and unknown. What are known things? The data. Data is known. But what is data? Known data means X and Y. They are given to us. That is what we are calling it as a trained data. With the help of trained data, we need to learn the weights and biases. Then only we can frame a equation. That equation we are calling it as a model. Once the model is ready, then we no need to worry about trained data. Then we can able to work with tested data. So fundamental concepts in machine learning. So whenever it depends upon the data, whether if I have simple data, I will fit a simple line. If I have a complex data, I will fit a complex curve. So how to learn that? See, ultimately learning a curve. If I have simple data which I can draw a linear curve, I will draw a linear line y equal to mx plus c. There are also mathematical equation learning m and c. If it is a non-linear curve, then I will have a high-level equation which we can learn by using numerical examples which you have studied, like RK method, Taylor series. So all those things can be used to find out the curve. If it is again high-dimensional, complex, we can use neural networks. But everywhere, whenever I say neural network, means it learned one mathematical equation. Whenever I say linear regression, means it learned a mathematical, it is representing a mathematical equation. So any model, whether it is a linear equation or a non-linear equation, a neural network, a binary tree, decision tree, I say that it is representing, it is abstracting a mathematical equation. There is an equation abstracted. With that model, we are making a decision. Okay? So fundamental concepts in machine learning. So as I said, we have to make a decision. So which are all the things we have? We have a classification problem, or we also have a regression problem. Okay. So classification problem, as I said, we can various steps we discussed. That's what we specified here. And also some type of data. So what about discrete and continuous data? Because ultimately the learning starts from data. So you must know what type of data you're going to deal with. So what is discrete data? Discrete data means countable data, which is not contiguous. Okay. And what about this continuous data? We cannot count it. It is continuous. Okay. So 181.5, 161.3. So those are called as continuous data. 7th step, 8th step. We cannot say 7.2 step. We'll say 7th step or 8th step. Okay. So here it is like height. Okay. Like how many runs. But age is contiguous. Age can be 23.5 years. Okay. So that is data. So now regression. So machine learning, regression, we want to do it. So we have given with some set of points. From this set of points, which represent weight, comma, height. Okay, we need to predict the five samples are given. We need to predict the sixth one. Sixth person height and weight. 6 to infinite set of points. Test points are waiting. We need to find out the heights. That means y values. Okay, so they given some set of points. right? That is data. See, visually it is a circle, but what actually it is? 10 comma, sorry, 100 comma 5.8. So what is weight? 100. What is height? 5.8. But visually it looks like a dot, but what actually it is a representing a numerical value. Like this, they're given some set of values. Okay, so what we need to do, this is the data point first step given, and what is the question we have? I have some set of points waiting. So those weight comma height, weight comma height. So those values you need to predict accurately. That is the question. So this is the data, and first this is the data, and we have a problem. So what is the first step we need to do? First, we need to find out what is the first step. So this is the problem they given, that they given the data and they given the problem. What is the problem? They want the height of unseen cases. They given 5 points. From these 5 points, you have to learn such that then from the 6th point, you have to tell me the weights. Then how to solve this? What is a step-by-step approach we need to solve? So when you want to predict a value, it is a regression, okay? Regression kind of a learning. So from data points, you have to do regression. So same, we need to find a curve. So you need to fit a curve. So once you learn a curve, then what you can do, this x is unknown point. So any unknown point, you can find out the value. So with the help of these circles or known points, once these are the known points here, this is called raw data. This is data. Here there is no learning happened. Here learning happened. Here learning happened. What's the difference? The curve. The curve I learned. The resultant of my learning is the curve. The curve, mathematical equation, the model, all are same here. So this is the resultant of machine learning. Once I do the machine learning, what is the advantage? I can get the value of the unknown or the unseen data. That is the power of machine learning. So see here. See here, I can fit a straight line, or I can fit a non-linear line. Non-linear line also I can fit, right? So anything is same. So same case. In this case also I can find out the value for a unknown case. Here also I can find out the unknown case. Then which one to select? This one or this one? Which one to select? Ultimately, the model which results in less error. There are multiple ways depending upon the data we have. Someone asked which one to go. So either you can go with a linear one or you go with a non-linear one. But ultimately, you have to choose only one best suited equation or a model, which is that one which is having the less error. So see here. Okay. So this is the thing. So okay. So having studied this one, so this and all we already discussed. So known training data. So we call these points as a training data, and this equation. By using this equation, we need to learn a model. And once the model is done, we can use the test data. Test data is a blue point. We can use the blue points to know the unknown data. Okay. So that is training data and test data. Okay, then, so what we do with test data, see here. So there exists a difference. As I said, for a test point, okay, for a test point, there this is the actual value. But my line, the predicted line, is a set of, the line equation is a set of predicted values. So for this unknown point, this is the point and this is the value. This is the value, x value. But originally, ground truth value is this one. So what is the difference? this one. Like this, the model which is resulting less error, we will choose as the best one. Okay, so this line equation contains set of all predicted values. Suppose I have a point here. Assume that the ground truth is here. Okay, that means this one. So this is the value, y value for this x point. But what is my predicted value? Directly go to the line, this equation, this one. And if you go to the y-axis, this will be my predicted value. So what is the difference? This much is the difference. This should be as less as possible. So the model which results in less error, we will select it finally. So like this, they explained. Okay. So now we are entering into this one. So we are going to study regression, logistic regression, names-based, classification trees, regression trees, and neural networks. So these are the things we are going to study now with the help of mathematical setup. So fundamental concepts in statistics. Okay. So assume that, see, now, what is the ultimate aim here? What is the ultimate learning? We have data, and what is our aim? What is the ultimate aim here? To come up with from data, we have to come up with the data, what we need to do? Come up with
Prediction.
for prediction, what we need? Equation.
Model.
What is model? Equation. So ultimately what we need to do is, from data, we need to check how I can come up with a equation. So how to frame an equation? So here I have data. So if it is linear, that's what we have seen. If it is linear, if it is tree based, or if it is neural network. So if it is a linear based, then we have linear regression based equation. If it is, then logistic equation, like this tree based neural network. So ultimate our aim is, if I have some data, if I want to solve a problem, this data I need to convert into equation. That equation I need to select based upon. So which technique I need to follow? How I can select? With the help of data. How my data is. If my data is linear, I can go for a linear. If my data is a non-linear, non-linear. More complex, I will go with a neural network. Now here we have a simple problem. What is that? So Monday, when we go to a pizza shop, Monday we got 21 fries. Tuesday we got 24 fries, and Wednesday we got 19 fries when we ordered French fries. Now the question is, Thursday, how many fries we are going to get? If we are going to get 40, we will go to the shop. If you predict that we are going to get 4, we are not going to the shop. So we are if it is winning case to us, we will go. If it is a losing case, we won't go. This is the problem. Then how to approach this? This is the problem, right? We have to predict. So here we have some training data. So what is the training data we have? So this is the training data. Okay, so from this training data, you need to come up with a model or equation so that it can answer this question. So ultimately, which model or which equation we need to select, it's all depends upon the data. Okay, so the ultimate aim is converting data to equation is called as machine learning. And obviously that equation should be optimal equation. It should not be a random equation. Y equal to mx plus c, x is known to us, y is known to us. In m and c, infinite set of values are there. You randomly select any two values, it becomes an equation. But does it solve the problem? What is the condition again? When we qualify a model, when we select a model, what is the qualification? What is the condition it has to satisfy? Accurate prediction. Accurate means the error should be as minimum as possible. That is the condition. The equation which satisfies that condition, we need to select. So ultimately, what is machine learning? Converting data to equation is called as machine learning. And what is this? This one. in advertisement, we'll see in the downwards condition. What is that condition? Optimal equation. Okay, so now we got about what is machine learning. So now this is the problem. Having this problem in the backend, we are going to study various techniques. The first technique what we are going to study is histograms. So we have some histogram. So what is a histogram here? So histogram helps us to plot if this is the data. Okay, so assume that data means it's for better representation we are using like this. So we have data. So from this data, okay, so same, this is data point, same here also we have like this 21, 24, 19. So like this we have, suppose this is the line from 0. So 21 we have some point, 24, okay, some 24, or else if I plot like this, okay, so 0, 10, 20, so 21 I have 1 point, then the second day I have 29, and the third day I have 14. Then what will be the value here? Okay, plot a histogram, right? So if we have some set of points from this point, from this chart, it is very hard to analyze the data, right? So now here also see at same point, suppose if at all points the same point, if I plot like this, 1 point above, 1 point above, but still here also a problem, right? So what we can do, this is the data we have. For better analysis, we need to convert this data, which is very complex to visualize, into this particular format. We call this as a histogram. So histogram we have this y-axis and this as x-axis. So suppose x-axis, suppose it varies from, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the points which belongs to same value we are putting like this. So now we converted the problem. Assume that this is the French fries problem. Okay, so one day I got these many French fries. Whatever it may be, shorter, taller, irrespective of the description, assume that some problem. It is representing some real-time scenario. So French fries on first day, French fries on second day, third day, fourth day, something like this. Okay, so now with this distribution, okay, with this distribution, what is the analysis we can do? Is it possible to solve our problem? The problem of French fries. What is the number of fries we are going to get on Thursday? This is a problem. We transform it into a histogram. Now, how this histogram is going to solve our problem? If so, how it solves? How it helps us to solve the problem? Mathematics. Okay. Very good. So any answer from the online participants? I have a problem. Problem means data. I have data. So I need to predict the fourth day or the fifth day how many fries I am going to get. Assume that like this I have some set of data. So that data I converted into a histogram. How does this histogram can help me or helps us to solve the problem? Anyone from the online participants? Am I audible to the online participants? Surya, am I audible? Okay. So see here, what is the advantage? Once we convert the problem which we have into a histogram, as one of the participants told us, here, based upon the distribution, what it tells, the majority of data. Suppose I've been to the shop. Okay, so how many times? So first time I got these many fries. Second time, okay, suppose like this. First day I have these many fries. Okay, second day. So like that. So how many days, depending upon how many days I've been to the shop. So these are all the fries, French fries I got. So now how I can solve this problem? So on an average, the next day, if I want to predict, on an average, it falls into this particular range. The chance or the probability is high that the next day, the number of fries I'm going to get like this falls into the, falls into this particular probability area, this particular area. So what is the probability that, so we can able to find out the probability which falls into this range. Okay, so and they discussed about the problems. Okay, so if we have less number of bins to compute histogram, we are not going to get variance among the data. If we have too much bins allocated for histogram, we may not see either too much of bins or too less of bins, may not give you the first-hand experience on how the data is varied in the how the data is varying. So you need to find about the optimal set of bins in order to find out the variance among the data. Once you find out the variance among the data, then the histogram will give us a probability around its mean that this one, that any missed value, which I want to predict, most probably that it falls into this particular region, because this is the most occurring scenario. So the problem, first simple problem, if it's a very simple problem, we are converting that problem into a histogram. And then we are trying to solve the problem. First approach, very simple approach. And how we are solving, again, we are depending upon the probability. So what is the probability? See here, intermediate representation, the problem we have, and intermediately we transform the problem like this. And it's look like this is a histogram. So it helps us to understand the trends among the data, how the trend is. Once we plot the graph, see here, the red plot, okay, estimate the probability that the next measurement, next unknown value, highest chance that it falls into this particular region. So on an average, it may be 4, or it may be 5, or it may be 3. Okay, so what is the probability that, see how many points are there? Total points are 19, out of which this is 5, 8, 9, 10, 12. So 12 points out of 19, that means 63% of chances that the unknown case falls into this region. 63% of cases, it falls into this region. So now see, mathematically, again, we are using this mathematics probability. Okay, so a simple problem, just convert into histogram. Based upon a histogram, you compute this one. If it is looks like a distribution, normal distribution, then apply the probability. So that 63% it falls into this region. And what is this? What is the probability of this particular falling into this region? What is the probability of this region? 1 by 19. Very, very less. Okay, like this. But the problem is the histogram helps to solve the problem if it is having complete filling of the data. If data is missing, okay, for the bins, then we may not completely depend upon histogram to get the predictions. Here we are getting the prediction, 63% it falls into this particular region. But sometimes here what happened, the bin is not filled. Okay, if bin is filled, we can use the histogram. Now, in these scenarios, what is the next step? Slowly, we have a problem. That problem, what is that? Monday. So Monday, this many fries, say 12 fries, 24 fries, 16 fries, Monday, Tuesday, Wednesday, what is Friday? So this problem we mapped into a histogram, and ultimately we taken help of probability to decide that how much probability that the next case will be in this region. But the problem is here, the histogram, all bins must have value. Then only we can able to find out the best probabilities. If it fails, what is the next solution? Simple problem. Now we are not entering into the linear regression or a decision tree. Simple. If I have simple problem, just map it to histogram, analyze the data, and apply probability. Suppose here we have this kind of problems. Then how to solve that? Anyone from offline, online? Now we don't worry about
Taking the data and average of the value.
okay. See, the average it's okay, but average again it will see the thing is if I take average, there are chances that it will be erroneous, right? See, suppose here also what happened. This is the data I have. What is the average here? Somewhere here average. So if I take average, this is the average, right? So in some case, sometimes what happens, average may be the best, but sometimes it may fail.
So three types of average: mean, median, and mode outcome.
More or less same thing, right?
Yes.
Then see, these kind of problems is well solved. We can solve it easily with the help of linear regression or other techniques, decision tree, etc. But we are going step by step. Okay, assume that we don't know linear regression, etc. So first we did the histogram analysis and we try to solve the problem, but the problem is we don't have much data. And what about next solution, next possible solution? And what is the target? What is the target here? Representing the data into a equation. So now, which are all scenarios where we have a ready-made equation? No, Karona, next, without doing anything, is there any existing facilities which we can use and map it to the existing data? So if we have an equation, if this equation I will map it to data, and this equation will become my model. I don't want to do any learning here. And then slowly we move towards learning. So first we did histogram. Histogram, there is no learning, just keep on mapping and then apply the probability. Suppose the problem is if I don't have much data, then the histogram is not optimal. Okay, that is a problem. Then how to do that? Now you think about the scenarios where the ready-made equation is available. If luckily my data maps to that particular problem, I can take that equation as my model. Yes. What she's telling is correct. Probability distribution. So probability distributions we have binomial distribution, Poisson distribution. So we have distributions with us based upon the problem. If my problem maps to a probability distribution, every probability distribution is having a mathematical equation. Then that mathematical equation will become my model. Second step, LKG to UKG. So a histogram is LKG. So now we move towards UKG. So what is happening here? So histograms probabilities anyhow we have seen. What is the range if any points falling into this range is 19 by 19, 1. Okay. Now, the problem comes that if you don't have any data here and that probability is 0, but in real time it may fall into this region. So histogram with insufficient filling of the bins are not accurate. So what we need to do is, say BAM. So what is the next step? We need to look into probability distribution. How my data is distributed. So if my data is distributed, suppose it's a binomial problem or a Poisson problem or a normal distribution, these distributions have ready-made formula. So we don't need to build the formula, just we have to cross-check whether my distribution follows which of the probability distribution, and that corresponding equation is my model. Without learning here. Okay. So, okay. So first we start with binomial distribution. Binomial distribution. So what is binomial distribution here? Two cases are there. Okay. Pumpkin pie, blueberry pie. Two pies are there. Now the question is, first imagine, now we are studying binomial distribution. Okay. So let's imagine we are walking down the street in Scotland and we ask the first 3 people. Okay. So what are the 2 chances when we use binomial distribution when the output is of 2 class, spam or non-spam? Okay. So 2 class problems, we can use binomial distribution. Okay. And now here, if you see, there are 2 classes. One is pumpkin and blueberry pie. And say 3 people, means total number of people we are asking is 3. Okay. We meet if they prefer pumpkin pie or blueberry pie. Now, assume that the probability based upon our extensive experience, okay, assume that 70% of people prefer pumpkin pie. Okay, so whenever I ask a person, assume that the probability that he choose pumpkin pie is some 0.7 and blueberry pie is 0.3. Like this, I ask for 3 people. I want to take decision from 3 people. Okay, so this is a 2-class distribution, either pumpkin or blueberry. What is the probability? Sum of the probabilities must be equal to 1. So assume that based upon the a priori, this is called a priori. So what is a priori based upon our exhaustive experience? The pumpkin is having 0.7 probability and the blueberry is 0.3. Now I'm asking 3 people. See, first person, if I ask, what is the order? The order can be, how many options are there? 2. If I'm asking 3 people. If I'm asking 3 people, what is the probability? What are chance? How many chances are there? How many chances? See here. First option. Okay. First game, let's say this. Okay. 2 options, right? So, see, let me come up here. See. 2 over 3. See here, the probability that the first person will prefer pumpkin is 0.7. Suppose pumpkin. Second person also pumpkin. So this one, blueberry and 2 pumpkin. What is the probability? Out of 3 people I'm asking, 2 has to say pumpkin. What is the probability? Okay. So the probability is like this. What are the chances? Out of 3 people, 2 people selecting this one. So first it may be a pumpkin, then this one. What is that? Pumpkin and first may be blueberry, next pumpkin. Next blueberry, pumpkin, blueberry. So this is the combination. Right? Is there any other combination left? 2 out of 3. So total 3 people are there. 2 classes are there. So 2 people has to accept 2 people selecting this one. What is that? Pumpkin out of 3. So these are the things. So what is the probability? This is one case. This is another case. This is another case. So if I add all these 3, what is the probability? 0.447. So what is that? Calculating and the probability observing that 2 out of 3. What is the problem? We are having 2 out of 3 people preferring pumpkin. Okay. So what is the probability? 0.3, 0.7. 2 out of 3. So this, it can be 2, this way 2, this way 2, this way 2. So what is the value? 0.44. So what is the formula we have? Out of 3, 2 people selecting pumpkin. What is the a priori probability? 0.7. So this is the formula. If you substitute, what is the value we are getting? 0.441. So what is the problem here? What is the problem? The problem is if at all, see, now what is this equation? This is the model. So what is the data we have? Out of 3 people, 2 people selecting a particular product. And for selecting a priori probability is 0.7, 0.3. In that case, 2 out of 3 selecting product, what is the probability? So we have a built-in formula. We are mapping this problem to binomial distribution. And binomial distribution, we have a formula. And that formula will be my model. Okay? So this is how we are mapping a problem to a equation. So ultimately, learning this equation is important. Here, there is no learning. We are just thinking from simple steps. From a data, how histogram helps. From data, where histogram fails. If histogram fails, what will be my next problem? Without learning anything, there will be a set of probabilities, out of which the first one is starting with only 2 class problem. So, okay, 2 class, binomial distribution. So binomial distribution is having a ready-made formula. So this can be my model. Next, if binomial distribution is over, okay? So same we have studied. Now, what is the problem with binomial distribution? See, the 2 is fixed, but the number of people we consider is more. Suppose 4 people, then 5 people, then what happens? It will be a problem. mathematically. See now, one more distribution we mapping. See here, if we can read an average 10 pages of this book in an hour, okay? Suppose at 9 o'clock, I studied 10 pages, okay? Next, at 10 a.m., how many pages we are going to read? This is the problem, simple problem. Last hour, I studied 10 pages. The next hour means in 10th hour, how many pages I'm going to read? This is a problem, okay? Then how to solve this? So, same, Poisson distribution will help us. Okay, see here. How this one helps? Okay, see here. The equation of the Poisson distribution is this. So, if I can read 10 pages, okay, 10 pages, okay, in last hour, what is the probability that I can read 8 pages the next hour? It's called as Poisson distribution. So Poisson distribution is having a formula. Wherever there is a formula, we are checking that that's our problem. Can we map it to that particular formula? Okay. So in this scenario, this is the formula. So if you substitute, okay, so this will be my problem, and finally we can able to get the probability. So what this value equal to this value. So here there is no learning. We have some problem mapping it to any of the probability distribution, because ultimately we have a data will have a distribution. That distribution can be represented with the help of a histogram fields, not much data, then we can map it to probability distribution. Again, probability distribution we have, it may be 2-class problem or many class problem. So 2-class problem we have binomial distribution. In these kind of cases, regression problems, we can use Poisson distribution. Okay, next one more set of distribution. Okay, so this is the formula we can use. Okay, so now same thing we also have for continuous data. Okay, these are for discrete data. Say when we say 8 pages, 10 pages, that is discrete data. Suppose if you have continuous data, what to do it? So although they can be super useful beyond reading of a lot of data, see, the histograms is having some problem, that is they missed out the data. Okay. So now, when we have continuous data, a continuous distribution we need. Okay. So in case of this one, discrete values, I can use either binomial distribution or a Poisson distribution. If my data is dealing with continuous data, age, okay, so all the height, okay, so those kind of cases, so what I can do is I can use a binomial, so this one, normal distribution. See here. So what I can do is, so like this, if I am dealing with continuous data, I try to fix a curve, the data which I'm having, I try to plot a curve. So if my data is like this, see here. So y side, we are calling it as a likelihood. We are calling it as a likelihood. And in these cases, we are calling it as a probability. So what is the difference between probability and likelihood? So when we are dealing with discrete cases, we are calling it as a probability. And when we are dealing with continuous cases, we are calling it as a likelihood, estimation of likelihood. Okay, that is also very important. See here. So when I have a point, see here, when I have a point here, most likely value is here, this one. Whenever I have point here, okay, there is very less, this one, least likely. Probability. Okay, so when the points, if at all, there is a higher chances that a point falls into any of the point, the data points falls into this region is very high. The points falls into this region is very less. So if from the data, if we can able to, from this data, if you can try to put a curve, a normal distribution, there are higher chances that, highest chance likelihood is that my next data, my unknown data is falls into this region. and very likely that it falls into this region. So now once I compute this likely region, then I, irrespective of the data, the next point, highest chances is that it falls into this region. Right? So when my, if I have a data which is continuous, and if I plot a Gaussian distribution or a normal distribution, then I come to know that what is the likelihood, the maximum likelihood. So the next occurrence will be at this particular likelihood. So if you missed out data is no problem. Why? Because that is very least likelihood of occurrence. Okay. So this one, third probability. First one is for discrete, we have two probabilities, binomial and Poisson distribution. For contiguous, we have this one, Gaussian, fitting a Gaussian distribution, and then we compute the likelihood. So we, from this data, we get the maximum likelihood. What is the next probability that where the curve fits into maximum likelihood? Okay. So this is fine. So again, we need an equation. So what is a Gaussian distribution equation? If my data follows a Gaussian distribution, what is the equation? We need to have the mean and the standard deviation. Okay, so X is the data we have, and when I plug in the data, I will get this value. So this value is my prediction. So if I map my data, if my data follows a Gaussian distribution, then I can take this equation as my model, and I can plug in the X values, and I can get the values, because mu, and again the formulas also available, how to compute mu and standard deviation. Mean and standard deviation we can compute from the data. We can substitute the mean and standard deviation here. This is the formula. Okay. See, now if I want to compute for X equal to 50, from the past data, I compute what is the mean value and what is my standard deviation. If I know these two values, and for unknown case, if I am substituting 50, what is the output? 0.27. It's a prediction, right? So what we are doing here, we are just mapping the data to the Gaussian distribution. So this is the Gaussian distribution formula. We are computing mean and standard deviation, and we are substituting any unknown X. To compute mean, mu, and standard deviation, we need what we need to compute mu and sigma. What we need to compute mu and sigma? What we need? Training data. So with the help of training data, we will come up with mu and sigma, and then once the equation is framed, we can compute any unknown values. Okay. So ultimately, the problem we can map it to either probability distributions. So what we have learned here, we have to map the data to either histogram or probability distributions where there is no learning. Just by observing the data, we can able to get the equations. Okay. So that's what we have done. Next, we are entering into linear regression where actual learning happens. So first step is, what is that? Building the histogram just by observing the data. There is no learning here. Or just to check whether your data follows binomial distribution. Just check whether your data follows Poisson distribution. Just check whether your data is contiguous and follows normal distribution. All these equations have their own distributions, have their own equations. Those equations will be your model. If it doesn't falls into this category, we will move to linear regression where our learning starts. Okay, so now time is 12:28. Sing, sir. 1 o'clock. 1 o'clock. Okay. We'll take 5 minutes break. Then you water the sir.
Yes. Okay.
welcome back. We'll try to close linear regression. Okay, it's already there. Now, are you able to see? Able to see slide, right? Linear regression. Okay, so we just reviewed without doing any learning. So how can we analyze data? So first one is mapping to histogram, and just map it to any Poisson distribution based upon the data. So here there is no learning. So first we look into linear regression. So as we discussed, linear regression is ultimately we try to fix a curve. Okay. So once we fix a curve, we can able to map it to any unknown case and find the error. So here, see here. So if I want to map a curve here, there are n number of possibilities. If by keeping the same, assume that these 5 are the points here. So we can have n number of okay. So the line can be in this direction. Assume that we have only 5 points. Okay? So I can draw a line like this, or I can draw a line like this. So I have some multiple options. So how to choose the best curve? So as I said, the line, the straight line is a set of prediction values, and those predicted values must be as close as possible to the actual values. So if you see here, if we assume that this is the best curve, then this is the worst curve. Because if we, the difference between the actual points and the these predicted points will be more. So here it is very less. Okay. So ultimately, without doing any random analysis, how to come up with the best curve fitting for this set of points out of n number of possible curves is what linear regression. Assuming that for the data is linear and we can able to draw a linear curve. Okay. So here, y equal to mx plus c. So if I want to predict height, so the y variable is what a dependent variable we want to predict. So weight is the independent variable. Okay, so the equation is height equal to sum m into weight plus c. So where m is the slope and c is the y-intercept. So here the weight is fixed and height is fixed. We need to find out the best set of m and c values so that the line matches close to the data points. Okay. See here. So this is a line equation. So once we fit a line, assume that same problem we have, the number of French fries we are going to get on Thursday. So these are the points. So assume that the first day we got 21, second day 24, third day 19, and how many we are going to get on the Thursday. So once we are able to fit a line, then we can map, we can project x value into the equation. We will get the corresponding y value. Okay. So curve fitting or model development or function learning is fitting this particular line, so that we can able to find the answer for what we are going to do it on Thursday. So as I said, the predicted line is a collection of the line we are going to fit is a collection of predicted points, and these are all the observed points. So how to select the best possible line? So by way, there are here we have y equal to mx plus c. We have infinite set of values, the best infinite set of values suitable for m and c. By altering m and c, we are able to get multiple set of lines as shown here. Okay, so which is the best fitting line to this set of points? So how to compute that? So there are metrics available. So those metrics are here. So what is residual or what is an error equal to observed minus predicted point? So what is the difference between my observed value, this is observed value, and correspondingly the line says that this is the predicted point. Similarly, this is the observed point and this is the predicted point. So the difference between these two we are calling it as a residual or error. Now, there is one more metric we are calling it as a sum of squared error or sum of squared residual. Is nothing but we are computing the square of the error. And if you add for all the data points, we are going to get SSR, where n represents the number of observations. Okay. So why we need to have do square on the error, or why can't we use the same this one residual error observed minus predicted? See, this is one of metric error, and here we are computing square of the error, and anyhow we need to add for all the data points to get some of the squared residuals or some of the squared error. So why we need to square? Without square, is there any impact if we don't square the error? Just think of, okay? So now, so first step is what? We have some set of points. So we fit a line, we have n observations. So when we fit a line, we have these three red points are n observations, and the line indicates the predicted points. The difference between the observed here, this is observed, and this is predicted. For each point, if we add, we get the error. And what we are doing here, we are squaring. So for this point, the difference whole square plus for this point whole square and for this point whole square. So if we add, we'll get the total error by this curve. Okay, that's what it is indicated here. Sum of the square of the error between the difference between the observed and the predicted points. Now, so first one is this one. What is that? Simple equation error. So observed minus predicted. And again, there is one more metric, SSR. These also having an issue. Can you able to guess what's the issue if we use SSR? Or why we need to square the error? Anyone from the offline? Okay. Just think of. So see, what the difference is, in case of any of the errors, the error is proportional to number of points. So that's what we are doing here. When we do summation, it all depends upon the number of points, where sigma varies from 1 to n, where n indicates the number of data points. As my number of data point increases, obviously the error increases, right? If I count the error for 3 points, and if I count the error for 5 points, so error counted for 5 points is always more compared to the error counted for 3 points. So the metric, if we use sum of squared residuals, varies from 1 to n. So here it depends upon n. So the error depends upon the number of points. Suppose if there is a model counting error for only one data point, and there is an equation or a model counting 100 points. So obviously 100 points model means outcomes more error compared to the first one. So how to compensate this? Very good. So what the next one is, we are just taking the division of the error by number of points. So I'm taking average error. So we are counting so that's what we are calling it as a mean squared error. So mean squared error is the best metric for the line which we fit to the data points. Okay. And what we are doing is we are dividing it by n. So means mean, we are computing the mean over the error. So when we are taking n, obviously it is independent of n. Now this is also having one more issue. Can you guess? See, error comes from either x or y. So n indicates x, right? So x means number of points. So x indicates number of points. So as my x increases, that means my number of points increases, error obviously increases, right? So to overcome the drawback, we are dividing it by n so that it will become a mean square error. That is related to pertain to x-axis. Now, is there the issue with y-axis also? What y-axis indicates? measurement. Okay, see here we are finding the difference. Assume that this is in, see here. Now, if I change the measurement, see here, if you have millimeters. So if you take millimeters, the difference is this one. If you have meters, okay, so if depending upon my x, means my number of points varies, error increases. And also if I change the metric in the y direction, suppose if it is in millimeters, here it is in meters. What we are doing it here, see, the error is in case of numbers 1 minus 3 2. Suppose if I am representing with 0.001 002 etc. In case of meters, the number varies. Okay, so here the error is this one, and here the error is this one. But okay, so this is very high error compared to this metric. So now how to work on this? In case of x, that means depending on the points, we are dividing by n and we are getting MSC. And how to work on this one? So again, there is one more metric called as R square. So R square able to deal with both the independent of x and y. So here, if you see R square, which can able to work on the metrics, the issue with metrics, mean square error, and this one. So millimeters and the measurement x-axis and y-axis. So what it is doing is, it is computing an average value of the metric y-axis. There's a curve, and for this curve, they are computing the difference. So it is computing the SSR, means SSR for mean for this particular curve and for the fitted line by mean. So this is the fitted line. For this fitted line, what is the mean? What is the error? And for this mean line, what is the error? So it is computing the based upon this formula. Now, what is the advantage here? So we are adding extra term. So based upon the line we fit, we got the error. Okay, the curve which we fit. And apart from that, to make it independent of the metric which we choose, the y-axis, so they computed an average y value, and for that average y value, again they are computing SSR. So SSR mean means the error from this 1.6 minus what we are getting from this, okay, divided by total is called R square. What this tells? See here. So R square value tells us the percentage of error around the mean shrank when we use the fitted line. So how much we able to reduce here, because see here we are using mean minus fitted line. So this is a positive value. So obviously how much the error got reduced when we from the mean to the fitted line is what the measurement. So if I use, see this mean is constant for any data, I can able to compute the mean and then find the difference. So I have an error based upon the mean, and I have an error based upon the curve which I built. Then what is the difference? So in this scenario, it is independent of x-axis and independent of y-axis, right? Because I'm considering the mean value. So how much it is, because if I consider mean value, then there is no metric. So if I have an error from mean, that is 1.6, and if I fit a curve, it is 0.5. So how much I reduced? Suppose if I have another line from here, again I will compute same set of values, then how much error it reduced from the benchmark. So the benchmark is what? This error, this line, the average of y-axis. So this is called as R square. Okay, so again we have three metrics. So based upon that, we can choose which is the best line we can fit. So if you want to summarize, what are all the metrics we use? One is simple, observed minus predicted. What is the ground truth and what is the predicted value? Second one is square them and add for all the data points. And if we divide by n, it's called as mean square error and R square also. So R square gives us how much the error is reduced, how much the curve which we fit reduces the error compared to the mean. Okay. So now we fit a curve. And then we found that what are all the metrics we need to choose. But to fit a curve, what are the important parameters we need to know? See, this analysis we did, assuming that we fit a curve, right? We done with the curve, and then we made the analysis of error, predicted my whatever may be the metrics which we have learned. So all these things, we assume that we fit the curve. But to fit a curve, what are things we need? Y equal to mx plus c. We need m and c. So if we know optimal m and c, then we can draw a line, right? And then we can decide which is the best line. But how to choose m and c, right? That's what we are going to study post lunch, and that is called this one, gradient descent. So gradient descent is an excellent technique which we use to select the m and c are real numbers. Real numbers means infinite set of values are possible for m and c. Having x and y fixed, we have m and c. So m and c are infinite set of values. So how to choose m comma c? Okay, so that's what we are going to study using gradient descent. Then we can say that a curve is fit, and then we can quantify the error of the line out of n possible set of lines. Okay, so now how gradient descent works, that's what we can see. How can we fit the best possible curve so that the curve which we fit for linear regression is optimal. Okay, that's what we are going to study post lines. Okay, maybe we'll meet at 2 o'clock. 2 o'clock. Any questions, any doubts still from the offline participants? Regarding curve fitting, linear regression, mapping from choosing the distribution, histograms. Fine, if there are no issues, then we can meet at 2 o'clock.